When I say people, I know a little bit of Brazilian, and then I say which words I know, which come from our dance. You will be laughing. Because the typical words we use are onde and chicote.
Chicote.
And you will be laughing.
Marcelo, tá no ar.
Because the typical words we use are onde and chicote.
Okay, so good morning. And on behalf of the graduate program in astronomy of the Observatório Nacional, welcome to the second day of our special courses, Ciclo de Cursos Especiais em Português, CCE. So since 1996, Observatório Nacional has special courses to provide to graduate students and postdocs a broad view of select topics in astronomy, astrophysics, and cosmology. Every year, specialists from different areas are invited to give a course in their field of research. However, for the second consecutive year, due to the COVID-19 pandemic, we decided to organize a compact virtual and very special version of our special courses. Thus, I would like to say thank you very much to all the professors for accepting our invitation to be a lecturer in our virtual CCE. So thank you very much, Dr. Alexis Finoguenov, our today's speaker, and a special thanks to the organizing committee, Dr. Daniela Lázaro, Dr. Simone Daflon, Dr. Renato Dopik, and also Dr. Jailson Canis. So let's enjoy the second day of our CCE. Okay, Renato?
Okay. Yeah, I'll just do a brief introduction because like the previous speaker, Alexis is one of these people that if you're going to be listing his CV, is going to take half the talk. But briefly, he finished his PhD in 1997 in the Moscow Institute for Physics and Technology. From there, he was a Humboldt Fellow in Boston Astrophysical Institute until 2000. Then he went to Max Planck, where he stayed for a significant time as a researcher in the MPE, and became assistant professor of physics at the University of Maryland, Baltimore County, and eventually went to got a position as a professor at the University of Helsinki, where he's been since then. So Alexis has been he has an extensive experience in high energy and also optical astronomy and techniques, among others. And he's being a member in many programs, ground-based and space, such as Athena, where he was the chair of one of the working groups, Cosmos, UKIDS, GOODS, CNOC, Dept, Locus, Aegis, CDFS, BOSS, Euclid, Rosita, where he was also chair of the cluster working group, Mosaic, Foremost, HSC, JPAS, where he is our current coordinator of a science working group for clusters and groups as well. And he's also the PI of the Constraining Dark Energy with X-ray clusters. It's a project that we are actually part of it, and the National Observatory. And he works in many different aspects of clusters and groups of galaxies, has made significant contributions in many things, in particular scaling relations between the physical parameters of the systems, and also evolution of heavy elements in clusters and cosmological constraints, among other things. So it's a very wide variety of contributions in the area of high energy. And today he's going to be talking a little bit, give a little taste of high energy for those who are not very familiar with it. And so hopefully next year, when everything's done, he'll come physically to the OM and we can have a strong interaction. So without further ado, I'll pass the word to Alexis.
Okay. So thanks, Renato, for inviting me, and thanks to all the people involved in organizing this course. I know it's very difficult to organize things in these times. So I have prepared slides that should illustrate you the topics of high energy astrophysics, and I hope you can see my presentation, the presentation mode, and I'm changing now the slides. So if it doesn't, oh, it doesn't change for me. Okay. Yes, it changes. I hope it changes for everybody else. There's something in the chat. Okay, that's from Simone. All right, yeah, you can, I can see the chat, so if you have some questions, you can put in the chat, I will see them. The topics that we cover in high energy astrophysics is the physics, they kind of come naturally from the processes you can study, and I try to cover like as a science topic more than a particular, let's say, a particular direction of research that, for example, I'm involved. So there's some topics that you might be, just because of some topics that you might be interested in, and you're more interested in how you would do that using high energy data. So so in principle, how do we decide for ourselves which wavelength you would like to work, right? You can consider rest mass energy, for example, right? And you can then compute what is the rest mass energy of a particle you're interested in. You can take an electron and get half a MeV. You can take a proton, get one GeV. So like an example, right? You can also say, well, what is kind of energies, let's say thermal energies of the particles I'm interested in, and you compute this like by taking this temperature, multiplying by the Boltzmann constant, and then you get, you know, typical energies related to the thermal energy you're interested in. You can also consider gravitational binding energy. You can consider atomic binding energy, molecular binding energy, and nuclear binding energy. So, and then if we start placing those energies next to that, you know, next typical wavelength or the typical energy of the photon, then you will realize that if you start from radio and end with the high energies, which are X-ray and gamma rays, then the processes that are uniquely in the X-ray and gamma rays are, let's say, you go from the energies of the electrons in the atom, you to the energy of the atomic nuclei, to energies of elementary particles. So so basically that kind of determines the main interest in studies using these wavelengths. And if you're interested in something else, like, you know, electrons, molecules, dust grains, then you select a different wavelengths. So that's how you naturally make your choice where you would like to work. So the definition of the X-ray astronomy. So just to I will be using Röntgen or X-ray. It's basically it comes back to how the rays being discovered. Initially, there were some rays that were not understood. They were calling unknown rays, X rays, and then Röntgen was a physicist who explained that. So and so that they are named after him. So typical wavelength range that are covered here is for 10 to minus 5 nanometers to 10 nanometers. And here in this plot, making it, you know, quite illustrative how you connect well, here is just listed the kind of nanometers, things in nanometers, how you switch from one field to another. Just the basic sorry, clicked the wrong thing for some reason. Okay, right. So on this plot, I'm giving the wavelength, frequency, Okay, with now energy and that you can cross-link what I'm saying, like things in the electron volts or kiloelectron volts when we talk about energy of the photon. You can understand that this is like, for example, 1 keV, which is in this energy scale is 10 to the 3 electron volt, corresponds to the wavelength of 10 angstrom, and that's the scale here in angstroms, not nanometers. And the frequency is kind of 3 times 10 to the 17 hertz. Okay, so these are the kind of typical values we work with. So usually we only use energy when we say EV, KV, MeV, GeV, TeV. So that typically we operate with something close to 1 keV, 1 GeV, 1 TeV. While in angstroms that will be progressively smaller and smaller values. Okay, where frequency is already 10 to the 10 to the 18, 19, 20, and so on. It's kind of not so widely spread. So we use energy, but one can convert. So when we study object at high energies, it's not necessarily that we study different objects. We can study the same object, but the things that we see are not the same as you see in different wavelengths. And here is an example. If you take an image of the sun, and here is this photosphere at 6,000 degrees Kelvin shown. If you start looking at what are the image of the sun at different, let's say, the different energies that correspond to different temperature, you can see that with increasing energy of the emission, you see more of the magnetic activity of the sun, you see more of the corona emission, and you see less of the photosphere. So, and that is a principle that is applicable to most phenomena, that you see the same object, but you see the different aspects of the same object. The big topic that we cover at high energies is let's say in the extragalactic astrophysics, is this big kind of circle of life, where we link our studies of the compact objects with their feedback, the effect on the growth of galaxies in the universe, that also affects the appearance of groups and classes of galaxies, which we can monitor through the study of the hot gas that populates the groups and classes of galaxies. And also we can see the winds escaping the galaxies, because they are hot and they emit an X-rays. And so this kind of creates this circle of circulation of matter, if you like, in the universe. So when we go into detail and say, well, okay, so I see emission, how this emission is produced, then we consider the processes that let's say dominate in astrophysical objects. So the typical density of the astrophysical plasma is low, and the free particle interactions, their probability is let's say proportional to density cube, and so they are kind of down weighted, and the The two particle interaction are the more typical ones, and we discriminate between the particle-particle interaction and the particle-photon interaction. I will not have time to explain all the processes that are listed on this slide. In initial plan for this 4-day lecture course was to actually explain all these processes. But I will explain just 2 examples, one of the particle-particle and one of the particle-photon interaction, just give you a feel of kind of interactions that generate emission. What are the processes? So the examples of particle-particle interaction typical is the so-called free emission, or Bremsstrahlung, and the Strahlung is the German word for radiation, and Brems is the German word for braking. So also braking radiation, if you like, and it's related to the change in acceleration of electron on the fly around ion. Then, so this I will explain in some detail. Of course, you can get line emission from an I should have, okay. You get line emission from the if the atom get excited after the interaction. You can get annihilation emission if the 2 particles annihilate. The particle-photon interaction can cause the scattering, and in which the photon either loses or gains energy, and therefore we can see that. The photon can also be absorbed by the particle, and then if let's say the photon field and particle field will get in equilibrium, you will produce black body radiation, and also you can do the pair production from the from this interaction. So I will just explain here the absorption as one of the examples of this interaction today. Okay, so just before going into the mechanism itself, just to give you some sense of what we are trying to explain. Here is a slide with the typical spectra, and I'm putting here on the top panel at the left this accreting black hole, and this is the Cygnus X1 black hole is the source in our galaxy, so it's a galactic source. X1 stands for that was the first X-ray source, and it kind of discovered in the constellation of Cygnus. So you see here some kind of continuum distribution of photons. So on the x-axis you see the energy in these keVs. So that's from which I already explained. You can link to wavelength or frequency if you like. So typically from 1 keV all the way to 10 to the 4 keVs, and you can see it has kind of bumps and has this kind of continuum. So these are kind of spectra that we working with in those accreting black holes, for example. Then in the supernova remnants, which is the slide at the bottom left, here again on the y-axis is the energy flux shown, just to see where the most of the energy of the object is emitted, and then on the x-axis we have the energy of the photon now in MeV, and it's log of it, so that's 1 MeV. It's exactly where the 0 is on this scale, So so the like QV scales would be like 10⁻³ typically. And there you also see that the emission is kind of continuous emission. They are shown as the strongest component. And then there are also kind of different parts of this emission shown also at very high energies here. Okay, so so going back to a few examples of explanation of some of this emission, just to get first ideas how certain emission is produced. Let's quickly consider this photoelectric absorption. The principle is quite is illustrated here. So the photon is interacting with the electron that is bound to the atom. Electron, when electron gets more energy than the binding energy, it escapes the atom, and this process requires a certain amount of energy, otherwise it's not going to happen. And exactly this energy, it's a resonance process, so its efficiency is quite high. And then with energy higher than this threshold energy, the electron will just take all the energy with it, and the whole gamma quant will be destroyed. So we can formulate that kind of absorption mechanism, write it as using this optical depth formulation, and then taking the exponent and the minus of this optical depth formulation, and then there in this tau, which is this optical depth, we do this integral of the cross section as a function of energy times the density of hydrogen, and then we integrate over the path that the photon travels. Okay, well, let me skip this and go immediately to the picture. So so basically this is like view of the universe through our galaxy. So it's called peering through the mud exercise, because of course before we can see external things, we see our galaxy. So our galaxy works here as an absorber, and in red here is the galactic disk, where then basically amount of hydrogen is high, and then this column density is high, which absorbs the X-ray. And then in the blue are the patches where this absorption is low, and these are the so-called extragalactic windows for X-ray astronomy. And in principle, they correspond quite well also to the optical windows. And in principle, we can work relatively well, not only in the blue, but also in the green zones. And so in principle, X-ray astronomy can come even closer to the galactic plane compared to typical optical extragalactic survey. Okay, so but just as for the optical astronomy, we also have extragalactic areas of the sky and galactic areas of the sky. So here I list the tool that can give you the absorption in towards any direction you might be interested in. There you will just give the coordinates and get the typical column density. So when your column density is of the order 10 to the 20 centimeters in the power -2, that is low. And when it gets 10 to the 21, that's where it gets high. And then right there in the galactic plane, it gets to 10 to the 22. And the data we use come from the radio 21 centimeter survey that basically measured the amount of hydrogen in our galaxy. In addition to hydrogen, heavy elements also absorb at, of course, at the corresponding energies, and this energy is proportional to the charge of the ion in the power of 5, and followed by this quick decay in the cross section from the edge. And putting it all together, if we plot as a function of energy, again in kilo electron volts, here this one is 1 kilo electron volt. The dominant contributor here is marked, and so compared to like the absorption solely by the hydrogen at the typical energies of X-ray, is absorption by all these elements that are listed here is much more dominant, and you can see by how much. And iron is also very important. So, but the main absorption happens at energies below 1 keV. So that's oxygen, carbon, nitrogen are the key elements there. So that's the kind of combination of what makes the absorption as a function of energy, but then you also here, if you can see on the y-axis, we weight this by the energy to the cube, which is just artificial thing. So it does drop as energy in the power of -3. Well, it's actually 3.5. Right, from according to the formula I just presented, but this is just to illustrate which element is a key absorber as a function of energy. Okay, all right. So so that was the one example of what forms the X-ray, X-ray spectrum. So because this is the process of removal of the photon, is a multiplicative process. So it basically, you put in a spectrum and then you see less of it, right? So you have to do a correction. If you don't have any spectrum passing through it, of course you don't see anything. And here's an example of the particle of the emission produced by the particle-particle interaction that is emitting. So that is the additive process. So it adds whatever is emitting beside is okay, and plus you can add this process, okay, and then you multiply by this absorption process. This is how things work. And the example here is this Bremsstrahlung radiation that is created by when the electron is passing by a charged particle. In this case is has a positively charged ion. In this case is a proton shown, and the basic principle is the emission of the accelerated charge and that is what basically in the foundation of why the emission is produced. And so here this radiation field is created by the charge Q, which is the charge of the electron, and then we have the basically the change in the acceleration term written down, the change in velocity. The full formula for the emissivity of such processes given here. It has this quantum correction because when the electron flies too close to the ion, you have to do quantum correction, so that's called Gauss factor. It's proportional to the charge of the ion squared. It has to have densities of electron and ion in it. And then it has this exponential cutoff at high energy, and this is due to the distribution of electrons over velocities with which it flies next to the ion. And there we take like thermal distribution, so we can describe the probability of finding an electron of a given velocity by the temperature of the medium. Okay, and so that's just a convenient way. And if you have different distributions, then you would have to like solve this equation yourself. And this is called thermal Bremsstrahlung. Exactly that it's an expectation from this Bremsstrahlung process on the thermal distribution of particles. So the spectral shape is illustrated here. We have on the left-hand side as a function of energy of the photon, we plot number of photons, and the what you can see here is that with the increased temperature of the plasma, your radiation becomes harder. It is harder at high energies. It's just because this exponential cutoff is happening at higher and higher energies. And if you just change the density of the plasma at the fixed in the fixed temperature, then you simply change the normalization of the component. So when we measure the spectrum of an extragalactic source, any source in fact, which emits according to this law, we can actually derive both the temperature of the medium and the density of the medium under some assumption of the geometry of the source. So it gives us quite a good handle on the state and amount of the plasma that emits this radiation. So here are some examples of this hot plasma. So in order to emit X-rays, the temperature should be quite hot, typically of the order of the energies we work. So if we work at keV, then it should be of the order of a keV. And so objects that emit at such energies are supernova remnants, for example. Here are the images of supernova remnants, the one by Chandra, there's some by Rosset, these are X-ray images. And they also emit, and the optical wavelength here is this Anglo-Australian telescope image of the supernova also shown. And then if you look at the spectra, which is this something with pulse height and counts per channel plot here, and this used to be pulse height in the sun at the beginning of the high energy era of satellites, because that's just the way they were recording the energy of the photon. But that's like an energy in keV, which is also given at x-axis plotted at top of the figure. So between 1 and 5 keV, you can see that it's not only like some kind of continuum, but there's also lots of lines. And so these are these excitation lines that I mentioned that also generated by this thermal plasma. And they have several, you can, for a given element, you can resolve two lines on this plot. I think you can see only for, well, you can barely see for iron, but you can see some for argon and calcium. You can see like a second line. And the resolution here is not really great, but just enough to start seeing these major lines. And these come from, one line is from the what we call helium-like element, and the other one is from hydrogen-like element. So the atom only having one electron left or having two electrons left. And they are different energies. And this ratio of these two ions also gives you a temperature of the medium under some assumptions. You can do collisional ionization equilibrium, for example, assumption. In supernova remnants, actually, the age of supernova remnant is how it basically tells you whether it is approaching the collisional ionization equilibrium or it's not yet there. So, and this whole science related to understanding this process there. And here are just more examples of supernova remnants. Here is the Cassiopeia A source. Its image of the source in different lines is shown. It tells you that the elements, they are not in the same place, they are distributed differently in the supernova remnants. And so you can see how the escape of elements after the supernova explosion proceeds in this object. If so, supernova remnants are the result of supernova explosion, and supernova explosion itself, well, this one part of it comes from what causes supernova explosion. I'm not going to touch on that, but the other part is what causes the supernova light curve, the light from supernovas. So the light from supernova is usually powered by the radiative decay, and the classical one shown here, for example, if you take the nickel 56 and then it decays into the cobalt 56 and that decays into iron 56, it has this typical lifetime of 111 days, and that powers the supernova. So the angle of the high energy astrophysics is that the same process that powers supernova, the same process produces gamma ray lines that basically, when you do this transition, you're not only releasing energy, you're actually releasing the line emission as a part of this process. So some of it goes into photons, some of this goes into let's say energy of the particle. It's like some positrons, for example, have to be created if you want to change the charge of the element, or if the charge of the element is changing as a part of this process. So these lines are predicted, and some of them are observed. And so this kind of so there's a link. So there's some people see the light of supernovae, and some other people see the gamma ray lines, and you have to see one should correspond to another. And okay, so these are the lines that are produced on the scale of, let's say, 100 days, and then supernova goes on, goes off. But then if you're interested to see how many supernovae there have been in the whole history of the of the Milky Way, then you're interested in the elements that would have a decay time of the order of the, let's say, the bigger the better, right? But of course, if it's too big, then you don't see anything, because then it doesn't decay practically, right? So the an element that led to some successful results is like this aluminium-26, which has a 10 to the 6 year decay time, as and the gamma ray produced at the energy 1.8 MeV. And that it basically averages out the history of supernova explosions in our galaxy over 10 to the 6 years. So the typical rate is like 1 event per 100 years. So basically you have 10 to the 4 supernovae contributing to the map that you can see with aluminium-26. And these studies have been made. So, so this is an example of how you link the gamma ray studies with the optical studies and what kind of angle you can see. Okay, so here I have some more examples of what you can study with X-rays. So here is the M82, and that is a starburst-driven kind of supermassive galaxy. And if we look at the spectrum that you can measure here in X-rays, so this is the kind of predicted spectrum that one could resolve with future instrumentation. And you can see that there's lots of ions they are emitting, and you can study how ions escape, how heavy elements escape the galaxy. So the elements that we can study in using this thermal emission of plasma, they are listed here. So from carbon all the way to zinc. And I think the current and future resolution doesn't quite allow us to study isotopes. Of course, when people do stars, they do very high resolution spectroscopy, and then they can actually see the isotope. So isotope is a cool thing if you're interested in a particular process that happens during the supernova explosion that produces these elements, because then it's kind of a footprint of the certain chains of element burning. Okay, so here we do not have access to that. So in a sense, we are not as good as our stellar people. What we can do, however, is to do like kind of general account of the elements in the gaseous phase. They are all ionized, and so the physics here is relatively simple. So it doesn't require typical modeling of stellar atmospheres to really determine the abundance, and so that basically our contribution is to determine the overall budget of this element production, which is also important when it comes to how you enrich the universe with metals. So this is where high-energy astrophysics contributes. And in this process, we discriminate several types of supernovae. So based on the difference in their metal yield, right? So we have so-called core collapse supernovae that primarily produce the alpha elements, the elements that which their number can be equal number of alpha particles. So oxygen is a primary element there, and then supernovae type 1a that produce that burn elements more. So all the oxygen is burned during the supernova explosion, and you produce more heavier imprint. So basically iron group there, and because you're very efficient into burning 2 silicons into 1 iron. So, but silicon is still left during explosion. It's not all the silicon is burned, but all the oxygen is burned. And then we also have the asymptotic giant branch that basically loses a lot of material from the star, and this way this material escapes the star and reaches the interstellar medium, and reaches an interstellar medium, and these are even smaller in terms of their atomic number elements that this process produces, from carbon, nitrogen, oxygen, that like the elements that are affected by this process. Okay, and so basically we have a grasp on this major process that produces the enrichment, and this is important, of course, when you try to understand the chemical evolution of galaxies. So when we look at the on the sky with, let's say, X-ray telescope, so we see this is like an empty field, typical empty field. This is the Chandra Deep Field South, one of the deepest fields. It's a simulation based on actual observations by Chandra. So what you see there is a lot of point sources. These are all point sources, and some kind of diffuse sources. So these are groups and classes of galaxies. So then AGNs have emission produced near the black hole, active accreting black hole, and the emission mechanism is there partially due to what we called compact emission mechanism. And compact means that the amount of photons per amount of baryons is very high, and that's the definition. It's called compactness. Okay, and then the emission of groups and classes is diffuse. It means that the amount of baryons is much larger than the amount of light in those systems, and they emit this Bremsstrahlung radiation. So we have objects on the sky, they emit according to this Bremsstrahlung radiation mechanism that I have described. They have this kind of spectra here shown. It's like a poor statistic, but that's right. Okay, so actually is, I think there's something wrong with this mixing. I think the you know, right, it's hard to see for me which one is what. And this anyway is quite noisy spectra. So it's on previous slides I had better examples that with line emission where you can see that this is a thermal spectrum, because it's not only continuum but also the line emission. When we study the black holes, we do not only see of course the continuum emission. We also often see a neutral line of iron, and if the material is engaged in the orbiting around the black hole, then this line gets distorted, and then we start seeing broad lines. So the broad lines in X-rays are related usually to the fast motion of the material around the black hole. Okay, so that's just well, that's more in an example of what you can see. I picked a few examples. Of course, it's not all the examples I had throughout most of them, just because there are too many for a single lecture, and maybe this is already too many. But I just have those left in the slides just for an illustration, since I was talking about black holes on a different different slides. And this slide illustrates this absorption process that I have explained. So, so basically, if you have particular viewing angle on this accreting black hole, then you all the radiation will be absorbed, and then after some point, then there are processes, other interaction photon particle interaction process that, for example, Compton scattering, that although it's like low probability, but the condensate is so large that even those processes start to play a role, and so that came to this name of the Compton thick AGN. So it's so obscure that the Compton scattering is going to be an efficient process. And Compton scattering is a scattering of the photon on free electrons, so it doesn't really require particular ionization stage of the material. And those sources, they well, people can still see that at very high energies. There are either through, let's say energy dependent of this Compton process, which is not so efficient once the energy of the photon comes close to the rest frame energy of the electron. But also, you often see the component that it gets scattered. So not directly emitted by the black hole, but is scattered by the material surrounding the black hole. And that component also is seen at hard X-rays, for example. Okay, well, I want to let's see, get to some different points. So I'll skip my examples because I think I had too many examples, and it doesn't really make sense to quickly go for them, because if I don't explain enough, then it's lost slide anyway. So one thing that I wanted to draw your attention is the is kind of what is the, let's say, why do we start seeing this phenomena, right? So basically, we have in the universe size of particle acceleration, right? And what are these? These are plasma jets and microquasars, plasma jets in active galaxies, for example, shock regions, and which have also working as a Fermi accelerator. We have strong magnetospheres that work on accelerator. So this leads to production of energetic particles. And once the particle is energetic, then it has several ways to emit or interact with the background radiation, so that we can see this effect at high energies. So in a sense, when we study the universe at high energies, we search for the size of particle acceleration, and that the picture that we see at X-rays is usually not so abundant with the details compared to the picture is in optical. It's just that because we only see the size of particle acceleration, and they are not that many, and the picture is boils down to, you know, black holes, as I said, pulsars, active galaxies, which again these are black holes, or in our galaxy, microquasars. So these are stellar mass black holes. Right. Okay, I'll skip that slide. And when these particles okay, so one thing is that you produce these particles, so you have these cosmic accelerators, And then you would say, okay, so how those are getting to be seen, right, by us, right? So I did produce those, accelerated those particles. Let's call them cosmic rays. So why don't I just see them? Okay. So the thing is that particle propagation is not direct. Particles propagate along the magnetic field usually. And so the typical picture is like this. So if you generate a particle, it will just go like mess around and then eventually escape. So when it comes to you, you actually have no directional information where it come from. But when these particles next to the source, they interact with the, let's say, interstellar medium. If we say it in our galaxy, so it's interstellar medium. Then there are additional processes that allows us to see those particles. Okay, so if you have electron positron, then if in the presence of magnetic field, they will emit synchrotron. In the presence of the interstellar radiation field, they will experience the scattering. It's called inverse Compton scattering, and you will also see it. They will directly interact with the gas and do this Bremsstrahlung radiation, like I explained. Of course, not the thermal one; it's non-thermal Bremsstrahlung radiation. And then if you have heavy nuclei, then they will interact with the gas. They do make the pi plus minus production that eventually leads to electron-positron pair. And then again, this will be secondary, so-called secondary electron-positron interaction with the gas, which again are the same as this primary. It also produced the proton-antiproton pair that can be detected by direct experiments. This BESS and AMS experiments are shown, and also so-called production of these light elements, lithium, beryllium, for example, that is done in the ISM on this by these energetic particles. So they and of course directly you have X-ray and gamma rays emitted during this acceleration mechanism. So these are our ways to kind of decipher the energies, decipher the processes that happen in the in these cosmic accelerators. And then the last slide that I would like to show is basically a kind of beginning of why do we need satellites and when do we need satellites to do our study. And the same process of absorbing radiation also happens on the Earth atmosphere. And here with the solid line, solid curve, we show at which distance to Earth you have to be, not to be absorbed by the atmosphere. And at the X-ray regime here, which is here at X, here, you have to be very high, okay, above 100 kilometers. So basically there, of course, satellites is the only way to go. Then if you go to a bit hard radiation, like gamma rays, then it's already possible to do observation from balloons. That's why they do it from balloons at gamma rays, and we don't in X-ray. And then at very high energies, you can use your atmosphere as a detector, because then this energetic gamma ray will interact with atmosphere, cause chink of light, and you can detect chink of light with optical telescope. It's just like you detect a light from a scintillator by photodiodes. So it's kind of your atmosphere is the detector for gamma rays. And in fact, the problem of the telescopes, you cannot put them too high up in the mountain, because then the thickness of the atmosphere is too low, and so your detector is not as efficient as a different position. So you have to be relatively low, but then on the other hand, this is optical telescope, so you want it to be not affected by all this light pollution stuff. So it's kind of very it's not so easy to place them, but there's a couple of places where people are building this telescope. So one actually is on La Palma, Canary Island, this MAGIC telescope, and then the CTA is built in Chile. Okay, so that's my concluding slide, and I hope you got some grasp on the topics that we cover at High Energy Astrophysics. Yeah, I tried to simplify that as much as I could. I hope it's not. I hope I managed to do that, and it's not a total mess in your head at the moment. So, but I think remember that if we look at the science of the cosmic acceleration, and important are the particle-particle and particle-photon interaction for us to be able to see that. And these are like the basic things. And if you remember that, then I think that's already good step forward. Okay. Well, thanks a lot to everyone for listening.
Thank you, Alex, very much. It was a pretty nice talk, and I think it's a great taste of the full course for next year. So we have some questions. I see Simone has your hands up.
Yes, I have a question. So one thing that always amazed me that how the universe looks different depending on the wavelength we observe it. So, and also the description and the understanding of the physical processes also have different levels of development and depending on the wavelength. So, but presently, what are the main discrepancies between, let's say, optical and high energy domains? What are you missing still?
Well, I think like the active, what we have in the high energies often is the search for dark matter decay, and this, of course, this is very new, and it comes back to this point that I said: this elementary particles should be seen at high energies because these are their rest frame energy and rest energy, and this so far did not yield any reliable detection, unfortunately, so we still don't know what is the dark matter particle, what kind of particle that is. I think that is the biggest unknown to me at the moment, right? So, and well, of course, many of the phenomena that, okay, so I can, for example, say that if you start counting how many supernovae you find, you will not account for the requirements of chemical enrichment. And so there is this topic of trying to search for supernovae, but this is easily solved when you look for this radiative lines from the elements. So you can at least validate that indeed the amount of radioactive elements ejected requires that many supernovae. I think that's the and well, also on the, I mean, we had some long-standing problems of measuring balances of elements in the gaseous phase compared to what you see in the galaxies, and basically the abundance of the gaseous phase always come low compared to the abundances you derive from the stellar population. And X-rays are not an exception from this. So, and their understanding why this is the case, I think that is important. And I think the current picture is that I think for a number of objects, the agreement has been found. And so this can observe some example of where a solution could be in fact found. So that's for example, this example. Well, on the studies of, let's say, active galactic nuclei, of course, X-rays are quite efficient way of finding objects, but you do not find the same objects as, for example, if you look for like high ionization state lines in the optical spectra. So there's a different objects that you find, and they populate different galaxies, and they are located in different parts of the logical structure. So yeah, so these are kind of examples I can give on the spot.
Okay, thank you.
Okay. Alexis, I was curious about one thing that it would be nice to know your thoughts about this, because the usage of scaling relations with clusters recently has apparently shown a huge geometrical anisotropy. We actually have one student, PhD student, is working in part on this. In the universe, they found by looking at temperature, luminosity temperature relations, they found anisotropy, cosmic anisotropy. How do you think that's reliable? Or I was wondering about their thoughts on this.
Okay, right. So yeah, so indeed, the method there consists of taking part of the sky, taking their groups and clusters of galaxies, and then measuring whether they would systematically deviate from the expected luminosity temperature relation. And this way, and then if you say, well, if they deviate, then you attribute this to the Hubble constant, then you would, those papers claim, then you find the Hubble constant to be different and in different directions. So these studies assume that the scaling relation, this relation between the temperature of the plasma and the luminosity of the whole object is universal. And there was a recent study which showed that if you take galaxy groups and clusters that are located in voids and compare them to other locations, so grouping like in superclusters, then you find that the scaling relations is actually different, because the object of a given mass in the void, it's only forming now, and so it's merging, has to merge, and because it's merging, its luminosity is lower than the object that merged a while ago, and because it was also emitting, it built up some cold material by cooling it down, and this material starts dominating the total luminosity. So basically, in order to do this study, I would highly recommend not to use the cool core emission, exclude it, and use the correct size luminosity temperature relation, and then you may still be subject to residual uncertainties, but then at least this is already slightly better. But it's quite a specific, of course, topic that that requires introduction of the scaling relation for galaxy classes, requires an explanation how gas is heated in galaxy clusters, how gas is cooled in galaxy clusters. This is in itself is like I have a full lecture on this that I might try to fit in a full course. But this is it's a big topic that I have not been able to explain today. So it's kind of a bit of the topic of today's lecture.
Okay. So I saw on one of your slides that you passed briefly there. There was a simulated region of the sky with Athena, I think.
Yeah. Right.
I was wondering if you can say a few words about how Athena is going and the improvement.
Well, okay. So I think Athena is entering the phase B. That's like a production phase, and we are fixing the parameters of the mission, and then so the mission itself will have a CCD type detector, which covers a large area, and it has this radiation stability, and also it's good for bright sources. You can do timing analysis and other things, and then there is the high energy, like a high resolution spectrometer with imaging capability, and that's XIFU. And this one will allow to study special result spectra, and that's quite a unique instrument. And in fact, I am well, my university is heavily involved in building it, and I'm also doing the science of the missing baryons, which is basically something I thought I would be interested in doing 10 years from now, because everything else will be understood. And so that is quite a unique instrument, and that's I think is a breakthrough. That's where the main breakthrough will be happening. So I think so for now we're just proceeding with this mission. I think the one caveat is that we are building mirrors that a factor of 10 larger than that anything that has been attempted before, and currently the focusing of these mirrors has not, like the optimal performance on the focusing has not been achieved. So what they have achieved is 10 arc seconds, and on the kind of characterization of the point spread function, and that is not great. And this will, of course, heavily affect this performance of the CCD detector. Some of the science they claim they could do, they won't be able to do. But for XIFU, our pixel size was 5 arc seconds anyway. So for us, there's actually no change. And this is a completely new regime where we are photon limited, not confusion limited. So I think for us, there's no change, and we just will proceed according to the plan. But that's kind of update that you asked for.
Thank you. So are there more questions?
I don't see other raised hands.
All right, if there's no, I'm going to use Alexis here to ask one more thing.
Okay.
So it was very interesting, this table there's sent there about the analysis of supernova remnants and the elements that you see. And I was wondering how reliable it is for those who want to match supernova yields with different models from what you measured in the supernova remnant, as opposed to and we have one student that's working this as well, looking at directly at the ICM, the final products of all supernova. When you have this huge time lags between, for example, one of them was aluminum that took 1 million years to become magnesium, and then eventually you see only magnesium. And if you see this in the final product, you'd input this in your supernova model, this amount of magnesium produced by, when in fact was not magnesium that was produced in the explosion, was aluminum originally. The nickel has a very short, nickel to iron, very short time scale, but some of them show they're really huge. And I was wondering how can they actually input this into the supernova modeling to predict the yields that you have?
Right. Well, as I said, that in principle, the best way usually is to look for isotopes that uniquely identify which reaction took place, because that helps to see whether in the models this reaction is properly introduced. And I think for example, we have this problem that silicon to sulfur ratios that we observe, they are not very well reproduced by the models, and the modelers are quite puzzled by that, because like the layers in supernovae that are burned to sulfur and to silicon, they are very close by, so it's hard for them to do something else than what they are doing, and yet we see differences. So so that's the but yeah, but in principle, I see the point that in fact indeed, with these metastable elements, production of metastable elements, and subsequent detection of the radiative decay can be a way to pinpoint some of these reaction chains, and indeed, people may get some clues on that. It's just that I think primarily only aluminium was a successful story. Mm-hmm. So I think maybe we need to improve on the gamma ray instrumentation in the future to get more of these decay lines into the picture, and that would be, motivation to that would be to understand better this scenario of supernova explosions.
Mm-hmm. Okay.
Yeah, good idea, Renato. Let's build a satellite.
Yes. The CTA is being built, I think. It's going to take forever to finish Cherenkov large array. But anyway.
Yeah.
All right. So any more questions? We are actually a bit past the time. But if there's a last question. Okay. So if not, then I'd like to thank Alexis again very much for your talk. It was a great talk, and we hope you can come physically to Rio next year to do the Rio.
I hope so too.
Yeah. Thank you very much, Alexis.
Okay, thank you. Okay, bye-bye.
Alexis.